Hi, welcome back. In this lecture, I want to give you an overview of the second module. So I want to discuss very briefly all the topics that we are going to study in the next few lectures. In particular, this new module is really about QPU instructions or quantum gates that are the building blocks to building quantum circuits. So the three topics of these modules are the following. So first, I'm going to introduce the so-called circle notation that is very useful pedagogical formulation of the state of the quantum bits or qubits. Right? So we will find them extremely helpful for express superposition and also information encoded in the phase of the quantum bit. The second part is really about going through all the different quantum gates. So these are the building blocks for expressing any quantum algorithm. So we're going to look at QPU instruction or quantum gates such as write and read. That means that initialize a bit and read or measure a quantum bit. We will spend some time in discussing the so-called Hadamard gate. That is by far the most famous important QPU instruction in quantum computing, because it's our gate to create a superposition of the state, so to reach this quantumness of our code. And then also we are going to look at some quite familiar gate operation like a NOT and some, for instance, gates operating on the phase of the quantum bit. We spend quite a lot of time on quantum bits that can operate on more than one qubit at the same time. The most famous is called control NOT or CNOT, but also Toffoli gates, Fredkin gates. So this is the second part about the formulation of QPU instruction or quantum gates. In the third part, we're going to look at the use of different quantum gates to create a very famous quantum circuit, in particular the Bell's pair circuit that you already seen in the assignment of the first module. We are going to look at the phase kickback circuit, and last but not least, the swap test. An important point of one of these circuits, for instance, the Bell's pair circuit, is that we're going to introduce the concepts of entanglement. Is one of the probably most counterintuitive concepts in quantum computing, and as important as the superposition. So we will spend a little bit time in trying to understand more what entanglement entails and what are the counterintuitive effects that entanglement has on quantum computing. So the very first topic that we are going to look at in the first lecture after this one is the so-called circle notation. So we are going to express the state of a qubit using the two circles. So the circle notation is nothing else than a graphical tool for visualizing and understand the superposition of the quantum bit before the measurement, so when we still have a superposition. We have two major quantities that we can identify in the circle notation. The first is the magnitude or the amplitude that is related to the radius and this area here. So the higher it is, the higher is the amplitude for that particular state. So in this particular case, you see that amplitude is higher for the zero state and smaller for the one state. So this is a higher magnitude. Also means that if we do a measurement, this will have a higher probability of measuring. The other second important quantities is called a relative phase of the state 1 with respect to the state 0. So this is a line, and we have an angle with respect to the line of the state 0. So in this case, the angle is 0, but it could be, for instance, 90 degree if it was like this. Throughout this module and the next module, we're going to use the circle notation to visualize the superposition and the relative phase of the quantum bits. You will see how powerful will be. Anyway, I'm going to spend a little bit time in the next lecture about this. This module is really about QPU instructions or also quantum gates. So in the textbook, you often find either QPU instructions or quantum gates. So QPU instruction is an instruction that is expressing the working of a given quantum gates. So why they are important? Well, they are extremely important because quantum gates and the combination of quantum gates in a circuit is a way of expressing a program in quantum computing. So whenever we want to express an algorithm, all the most important algorithms in quantum computing are expressed using gates and circuits. So if we want to express an algorithm or write the code, what we're going to do is actually to write a circuit that will consist of the basic building blocks that are the quantum gates or QPU instruction. So this is very similar and akin to classical computing, where, for instance, we can express an addition as a combination of AND gates and other additional gates. However, the major difference that we're going to use and exploit is that these gates and circuits are quantum, right? So we will need to obey to the laws of quantum computing. In particular, the fact that we're going to use a quantum bit or qubit instead of bit allow us to access this very powerful concept that is a superposition of state. Before the measurement, our bit can be in a superposition, so we can measure either 0 or 1 according to a certain probability. The circuit that we're going to use for expressing the algorithm is just a formulation of a successive transformation, also called the QPU instruction, on a qubit system or on a multi-qubit system. So except for the read measurement operation, QPU instruction must support a unitary transformation. In the first module, we look at the transformation that are quantum. We say that they must be expressed by a unitary matrix or unitary transformation. What does it mean? Well, the first property is that each quantum gate must be reversible, because it must be unitary. And remember, the first property of being a unitary transformation is to be reversible. So we will need to be able to go back and forth from an input to the output of the quantum gates. So it turns out that many classical gates are not actually reversible. So think about the AND gate, right? So you have an output that is 1. You don't know what is actually the input. So we're going to work on quantum gates that are actually must be reversible. The other properties that any quantum gates must satisfy is that quantum gates must preserve the geometries. And this is translated to the fact that whenever we do a transformation on our state vector, the total probability expressed by the quantum vector must be equal to 1. Both input and output must be classical. So a very simple example of a program, an algorithm to generate a random sequence of 0 and 1s is expressed by this quantum circuit. So this is very simple. So we have a QPU instruction that is actually writing the values of a classical bit. That is, for instance, our C0, C1 will be in this case 1 and 0. So this is a quantum bit, but also a classical bit, and we can initialize. We apply a transformation. In this case, I'm using the Hadamard gate. That is a gate that is used to bring the bit into equal superposition of state 0 and 1. Do not worry about Hadamard gate. We will spend one lecture about it. But I can anticipate that the results of this will be something like this: 1 over square root of 2, 1 over square root of 2. Do not worry about this yet. We're going to spend one entire lecture about the Hadamard gate. At this point, we have an equal superposition of state 0 and 1, and we can make an operation on read, because the equal superposition 50% of the time we will measure 0 and 50% or 1. So what's the most important concepts of this slide? Well, the most important concept is that we are writing a quantum code by defining the quantum circuit. So whenever somebody asks you, how do you write a quantum code? The answer is writing code by providing a quantum circuit that then I run on a quantum computing. So this is a summary of what just said. Whenever we run quantum algorithm or quantum code, a quantum program, a quantum computing, this means that we formulate our program as a circuit, and then we offload the QPU. We measure, and the measurement of the execution of our quantum circuit is the output of our program. I want to give you just a flavor what it means when we program an algorithm or a code using a quantum programming framework like Qiskit in this case. Well, as I told you, what we do is actually define a quantum circuit. After importing the modules for the Qiskit, what we do, we just write our code that is in this rectangle. We define a quantum circuit first with the 1 qubit. We initialize in state 1. That's the function, the method to initialize to state 1. So it's 0 and 1, so that's corresponding to have all the probability of measuring 1. Then we applied to this qubit the Hadamard gate, and then we actually measure. So whenever we want to write a quantum code, what we do, we actually express a quantum circuit first. There are also a possibility to actually visualize once we define our code that is quantum circuit, and this is the way that we do in Qiskit. So we import the correct methods for visualization, and then we can simply call the methods to visualize in Python, the quantum circuit using the Qiskit framework. Then we have a number of different functions that are needed to actually run either on a quantum computer or on the simulator, like in this case. In this case, I'm using the Qiskit Air simulator, and then I do a transpilation processor that is just a source-to-source for the source-to-source transformation to run quantum simulator, and then we actually run it and we get the results. So sometimes will be 1, sometimes will be 0. Finish up with this introduction of this lecture. This is probably the most important slide that I want you really to reflect in this lecture. What I want you to think about is really about the power of using quantum gates abstraction. So quantum instructions and quantum gates are very, very powerful abstraction that allow us as a computer scientist to focus on only on the development of the algorithm without actually worrying about how this Hadamard gate or the qubit is actually implemented, right? So we have the abstraction of the qubit, we have the abstraction of the Hadamard gate, and we know what is the Hadamard gate transformation, what we can expect. So we know what is the semantic of a Hadamard gate, and we do not care, how this Hadamard gate has been implemented, either superconducting, ion trapped, neutral ion, and all the different technologies. So we do not care, for instance, that a certain microwave has been used to change the state of the quantum bit to implement a Hadamard gate. So this is very, very powerful tool. So as a computer scientist, we just focus on the Hadamard gate. We're going to use this abstraction to express our algorithm. And this allows not to focus on how this Hadamard gate is actually implemented at the lower level. So users can design algorithms without the need of understanding the underlying technologies. So for instance, the gates are implementing quantum hardware as pulses, microwaves, lasers. And these allow us to have a very, very portable in implementation. So the portability of a quantum circuit is given from the fact that we are relying on abstraction, that are the QP instructions, the quantum gates. This is the last slide. So my lecture, we will start first discussing the circular notation, that is very pedagogical formulation of the quantum bits that we are going to use in this course. We are going then to describe a number of QP instructions / quantum gates that are the building blocks for expressing quantum algorithms. And finally, we're going to see these QPU instruction quantum gates in use as a powerful abstraction to hide the complexity of the quantum hardware implementation. And we're going to see using at least 3 very important quantum circuits, the Bell's pair, the kick phase, and the swap test. Talk to you soon.